At this point in your study of physics, you will likely have heard of gravitational potential energy before. And you've probably looked at gravitational potential energy in the context of, say, an object near Earth's surface, and as it gets raised up, its gravitational potential energy increases, and as it gets lowered back down or falls down towards the surface of the Earth, its potential energy decreases. So the formula you would have used in that situation is this guy right here. Potential energy is mgh. Okay, m in this case is the mass of the object being lifted. G is the gravitational field strength of whatever planet you're on. And h is how high the object has been lifted. Now, one thing we should note about h is that h can be measured from wherever you want. So, for example, if you hold an object right now out in front of you, wherever you are, maybe the first place you'd think to measure the height of that object from is from the floor underneath you. And you certainly could measure h from there. But you might also think to measure h from the ground outside whatever building you're in, and you could measure h from there. But then realizing the ground has different heights at different points on Earth, you might think, you know what, if we're going to pick one place and always measure h from there, maybe we should pick sea level. And you could totally measure h from there too. The reason it doesn't really matter where you measure h from is because generally we're not interested in just knowing the gravitational potential energy of an object, and that's it. Generally, we're interested in how the gravitational potential energy changes. And if it's the change you're looking in, where you're measuring h from doesn't matter. If you take that object and lift it 1 meter higher than it used to be, doesn't matter whether you're measuring h from sea level or the ground or the floor, you're going to see that h change by 1 meter no matter what. So h is the height of the object, and we can measure it from wherever we want. All right. So that's just kind of a review of what you've likely learned so far about gravitational potential energy. And that works well in a scenario where little g is constant. If I'm going to use this formula, I have to have a number for little g that I can plug in here. So I need to have one number that I know I can sub in. But if we're looking at a situation where little g is not constant, that's going to be a problem. So let's say instead of taking that object in front of you and lifting it up 1 meter, let's say we now lift it up so high that it's above Earth's atmosphere. It's now in orbit. So whereas little g used to be, roughly 9.8 when the object was near you on the surface of the Earth, now little g is going to be a different value up above the atmosphere when it's in orbit. So it's not clear what we would put in for little g. So the problem we're running into here is that little g depends on the mass of the planet and the height of the object, or how far we are from the planet's center. So I'm going to have to adjust this formula to account for the fact that little g can be many different values, to adjust for the fact that little g can depend on mass of planet and also how far we are from its center. So let's see what that would look like. Let's start with the same formula again. Potential energy, or gravitational potential energy, equals mgh. And now I'm going to rewrite it, but I'm going to sub in for little g the formula we have for little g. So little g can be calculated as m big G over r squared. So this is the exact same formula I just had. Here's my m, here's my h, but in place of little g, I've put the formula for calculating little g. Now let's note, we've got a couple of m's here. This first m is from here. That's the mass of the object being lifted. This second m that we've just introduced over here, that's the mass of the planet. So let's make a note of that. Okay. So in this formula, I've got a couple of m's. They're different. One's the mass of the object, one's the mass of the planet. And I've got a couple of distances. This guy is the distance from the planet's center, and that's used for calculating little g. And this guy is how high the object is. And that, remember, can be measured from wherever we want. So what I'm going to do, just to simplify this formula a little bit, is to make these two sort of play nice together. To make it so they're actually measuring the same thing, I'm going to choose to measure h from the center of the planet as well. Right. R is the distance from the center of the planet. H is the distance from wherever we want. So if we choose that wherever we want to be the center of the planet, R and H are actually the same value. Okay, so what does my formula become now then? There's that m. There's that other m, my big G. And because R and H are now measuring the same thing, this H cancels out with one of these R's on the bottom. I can even sort of show that this way. That and that will cancel out. So I have a formula that looks like that. And again, because these two m's are different, the first one is the mass of the object being lifted. The second one is the mass of the planet. I should probably give them slightly different names so I don't get confused and think I can cancel them out or combine them together. So as we've been doing, I'm going to call them M1 and M2. So this is sort of the essence of our new formula for potential energy, gravitational potential energy, that we can use when little g is not constant. I'm going to write it out again just one more time sort of at the bottom here. Now, there is an issue here. Our traditional understanding of gravitational potential energy is that as you lift an object higher and higher, it gets more and more gravitational potential energy. And that's pretty fundamental to the understanding of potential energy. But that was because in our old equation, H was proportional to the potential energy. Because of the way the equation was organized, if H got bigger, PE got bigger too. But in our new equation, that H kind of got canceled out. And now the thing that's replacing H, R, is actually in the denominator, whereas before H was in the numerator. So what that means in this formula down here now is that as we lift our object further and further from the center of the Earth, R gets bigger and bigger. But because R is in the denominator, that means the potential energy actually gets smaller and smaller. That is going to be problematic. If we have a scenario where the higher I lift an object, the smaller its potential energy becomes, then it starts to look like we're breaking the law of conservation of energy. I could do a lot of work. I could put a lot of effort transferring energy to this object. As I lift it up and up and up, and energy leaves me and goes to the object. But then if I end up with less energy in the object than I started with, it looks like I'm destroying energy, like energy is leaving the universe somehow. And we absolutely cannot break the law of conservation of energy. So what we're going to do to make it so our new formula respects that, we're going to throw a negative sign in right in front of it. So now, as I lift an object higher and higher, R gets bigger and bigger, which means this whole number here gets smaller and smaller. But because this number is now negative, I have a smaller and smaller negative number, which means I actually have a larger number. So as R gets bigger, potential energy gets larger, gets bigger as well. But it gets bigger by being less negative. That sometimes takes a little bit of getting used to, but it's important. And the goal here was not to do sort of a rigorous proof of this new formula. The goal was to just sort of give you a sense of how this formula might come about and provide an opportunity to sort of look in depth at a couple pieces of it. So let's write that note down about that negative sign. The negative sign makes it so that potential energy increases as we do work. If potential energy were to decrease as we did work, then we'd be violating the law of conservation of energy. So I'm going to put a box around this because this new formula is going to be important for us. Now, up until now, whenever we talked about gravitational potential and energy, we had to choose a reference point where the gravitational potential energy was 0. This was where we measured H from, right? This is sort of referring back to our original formula here. And I said, you could measure H from the floor or from the ground or from sea level. That became our reference point. And if an object was at that height, H was 0, and therefore potential energy was 0. So we need to have a reference point for our new formula as well. And one thing that's nice about this new formula is there's a really obvious place that sort of jumps out at us for where potential energy should be zero. In our old formula, everyone could kind of pick their own place. In our new formula, there's one place that we're all going to stick with. So what is this very obvious reference point that we will use all the time? Well, looking at the formula, you can see that there's only one way to make this be zero, or to make it be really small. That's kind of a hint. If I have a certain object and I'm lifting it above a certain planet, those two numbers, the M1 and M2, are fixed. Big G is fixed. So the only thing I can really play with is R. So we got to ask, what can I do to R to make this whole thing go to zero? Well, zero is a small number. And we already said that by making R bigger, this number here gets smaller. So if I want that number to be so small it becomes zero, I have to make R as big as I possibly can. And what could possibly be bigger than infinity? So when R is infinity, meaning I lift this object so high that I couldn't possibly lift it any higher, it's infinitely far away from the planet, that is where potential energy is zero. Now, to help illustrate this, I think it's useful to draw a little graph. So what we're going to do is a graph of, and we're just going to sketch this, potential energy versus R. So again, let's consider a scenario where M1 and M2 and big G are all fixed, and we're just changing this on the x-axis to see what happens to this. So basically what I have is y is something over x. Y equals 1 over x, you can think about, which would have a shape kind of like this. But because of this negative sign, it actually gets flipped around the x-axis. So my graph looks more like this. So that's roughly what our graph of potential energy versus distance looks like. And you can see it sort of has two asymptotes, a vertical asymptote over here and a horizontal asymptote over here. And that horizontal asymptote is exactly what we were talking about in this point over here. You can see my graph is getting closer and closer and closer to zero. My potential energy is getting closer and closer to zero. And although it'll never actually get there with any achievable value of R, if I could take R and make it all the way out to infinity, that's where this line would hit the x-axis. And that's where my potential energy would be zero. So let's kind of recap what all this means. It means that whenever objects get closer together, the potential energy between them decreases. That's just like what we are used to from our previous formula. The potential energy will always be negative. That's a new idea, but I think we can live with it. And zero potential energy happens when the objects have escaped each other's pull by being infinitely far apart. Okay, so let's look, with this in mind, let's look at a problem or two. Now, one thing I'll say is, you might be thinking about this and saying, well, you can never have two objects infinitely far apart because the universe has a finite size. So to take two objects and put them infinitely far apart, we'd have one of them would have to be outside of our universe. But as I've said a few times, part of being a good physicist or a good engineer is not always about being able to solve the problem exactly as it is, but about being able to figure out what simplifications you can make so that the problem is easy to solve in a way that gives you an answer that's very accurate, if not 100% correct. So one great example we often use is neglecting air resistance. Anytime anything on planet Earth is moving, there is air resistance. But in your physics career so far, you've probably ignored air resistance almost all the time. It's there, but it's small. So you say, it's small enough, we're just gonna say it's 0. And we can get really accurate results that way. Same thing here. If two objects are really, really far away, potential energy is not gonna be exactly 0. Right? Because they can't actually be infinitely far away. But potential energy is going to be pretty close to 0. So this is a situation where we can just say, it's not exactly 0, but it's really close to 0. I'm just going to pretend it's 0, and I'm going to get a really accurate answer, even if it's not 100% accurate. All right, so looking at an example here. A 2,500 kilogram satellite is in orbit 3.6 times 10 to the 7 meters above the Earth's surface. What is the gravitational potential energy of the satellite coming from the gravitational force of Earth? Okay, pretty simple question to start with. We're just going to sort of plug and play with our new formula. So gravitational potential energy is negative m1, m2, big G over R. Probably the two most common mistakes people make with this formula is they realize it looks a lot like Newton's universal law of gravity, which is m1, m2, big G over R squared. So they tend to just kind of write it like that instead, meaning they forget the negative and they often square R, even though it shouldn't be squared. So keep those in mind. Okay, so in this case, M1, let's call that the mass of my satellite. 2,500. M2, mass of Earth. Big G, I won't bother writing it out. It's like pi, we all know what it is. I'll just write the symbol for it. And R. So R is the distance from the center, or from the center of gravity, if we're being specific. So if this is the height my satellite is above Earth's surface, then R is going to have to be that distance plus Earth's radius. So R is going to be 6.38 times 10 to the 6. There's Earth's radius, plus 3.6 times 10 to the 7. And, embarrassingly enough, I have just made one of the key mistakes I warned you about. I didn't square R, so that was good, but I did forget completely about this negative sign. So I'm going to have to adjust that right now. There we go. Okay, so if we plug in those numbers, we should get negative 2.3490 times 10 to the 10 joules. And I'm keeping a few extra sig figs here. I'll go with 5 because I'm thinking a little bit ahead, and I'm going to actually want to refer back to this number and use it again later. Okay, so box around my final answer here. Again, this can feel pretty weird, calculating a potential energy and finding out that it's negative. It's probably the first time that's happened since you've been studying physics, and it doesn't sit well with some people. So let me say a couple things to try and ease your anxiety about that if you have any. One thing I'll say is you probably haven't seen a potential energy that's negative before, but we totally could have created one, even with this formula that you're used to. Remember I said how we could measure that H from anywhere we wanted? From the floor, from the ground, from sea level. One of the places we could have measured H from, if you're holding an object out in front of you, is from the ceiling above you. So that object, although maybe it's 1 meter above the floor, it might be negative 2 meters above the ceiling. So its height, if we measure it from the ceiling, is actually negative, which means we would get a negative number for potential energy. And that would have been totally fine. Most people tend to not measure things, heights from the ceiling, but there's no reason we couldn't. And if we did, it would be totally fine. Again, because it's usually the change in potential energy we're interested in, not the actual value. Measuring it from a height above where an object is and getting a negative number would be totally fine. The other thing I'll say to help you be okay with this negative potential energy stuff is that potential energy energy itself in all forms is not something that exists per se. It's more of an idea. And maybe an analogy I'll draw here is with money. Coins exist. Let's say you have a certain number of $1 coins, of loonies. You might have 10 loonies, you might have 5 loonies, but if you tried to tell me you had negative 3 loonies, I'd call you out on that. Because loonies are something that actually exists. They take up space in our universe. They have mass. They're made of atoms. It's not something that you can have a negative number of. So having a negative number of physical loonies is not possible. That's why, if we think more in terms of scientific things, having a negative number of protons or a negative number of neutrons is not something that should be doable. And if I told you the number of protons in something was negative, you should be very skeptical. But energy isn't something that takes up space or has mass in our universe. It's an idea. So rather than being like coins, energy is more like the idea of money itself. So if I told you I have negative 3 loonies, that sounds weird. That's not possible. But if I say I have negative $3, that makes more sense. If I say I have negative $3, you might think, okay, that sounds weird, but I think I get what you mean. It means you're in debt. You actually don't have any money. In fact, you owe someone $3. So think of protons and neutrons as kind of like coins. They're actual things that exist in the real world. And think of energy more like money. It's an idea, and it can totally be negative. When energy is negative, it basically just means it was taken away from something. All right, so let's look at the next example that kind of builds on this first one. What is the total energy of the satellite in the previous question? Well, remember there's different types of energy. There's kinetic and potential. So I think what we're looking for is both of those added together. So total energy is going to be potential energy plus kinetic energy. Well, the potential energy of the satellite, we just figured out, negative 2.3490 times 10 to the 10. And the kinetic energy, well, we could calculate that. But we probably have to make some space for that. So let's do that somewhere else on our page. Well, we know the formula is 1/2 mv squared. And I know the mass of the satellite is this number up here. I just don't know the speed of this satellite. But you can hopefully recall from earlier that when something is in orbit at a certain altitude, there's basically one speed it can have. And if it goes faster than that speed for that given altitude, it'll float off into space. If it goes slower, it'll crash down into Earth. So there should be a way for us to calculate the speed of this satellite. So let's do that over on the side here. So the key thing about satellites is they are in a circular orbit. So we can use a circular motion approach to solve for things about them. The force acting on a satellite, there's only one. It's the force of gravity, and that acts as the centripetal force, giving a centripetal acceleration. The force can be calculated as m1, m2, big G over r squared, Newton's universal law of gravitation. And if I'm trying to find a formula for the speed of this object, I'm going to pick a formula for AC that has v in it. And that gives me, or leads me to, v squared over r. So that should help me calculate the speed of the satellite. Let's just see if we can do some simplifications. This m on the right-hand side is the mass of the satellite, so I can cancel that out with this m. And if I multiply both sides by r, that cleans things up a bit. This r will go away, and one of these r's will go away. Then I can rearrange for v, and I get m2 big G over r equals v squared. And then I can just square root both sides to give me the actual v. And maybe I won't, in an effort to sort of save some space, I won't write all the numbers in here, but m2 is going to be mass of Earth. Big G is the same value as usual, and r is going to be what we had up here. So this really kind of mirrors the formula we had before. M2 is going to be that guy, r is going to be that guy. So if I punch that in, I get that v equals 3,065.3 meters per second. Again, I'm keeping a few extra sig figs here because I'm going to use this number again later. So, a little bit of circular motion helped us find the speed of this object. The whole reason we were doing that is so we could plug it in here to find the kinetic energy. So let's go back up and do that. So m, the mass of the object, 2,500 kilograms. That's from in the original question, back up here. And v, 3,065.3 squared. Crunching those numbers in my calculator, I get that V is, or that the kinetic energy is 1.1745 times 10 to the 10 joules. So, quick recap. We had this satellite. It was a certain mass, certain height above the Earth. It was in orbit. We found its potential energy. Then we were asked to find the total energy, which meant we need to get the kinetic. We now have the potential energy and the kinetic energy, so we're going to add them together to get the total energy. But first of all, I want to point something out. So this was my potential energy. And this is my kinetic energy. Do you notice anything about those two numbers? Well, it turns out that this number here is exactly twice this number here. Which seems a little weird given the amount of math and number crunching we did to get to this point. Turns out that's not a fluke, and we'll talk more about that in a second. But for now, let's just finish this problem. So this means the total energy of the satellite is negative 1.17 times 10 to the 10 joules. Again, a little weird to have a negative number for energy, but totally fine. And in fact, it's expected at this point. Now, let's dive into this idea a little bit more, that this potential energy number was exactly twice the kinetic energy number, and it was negative. I said that wasn't a coincidence. Let's see if we can prove it. So, if I have a satellite, that means I have an object in orbit around another object, which means I'm dealing with circular motion. So we can start with a circular motion sort of setup for solving this problem, or for looking at the satellite. Right, and this will look familiar at the beginning because we just went through this process in the last question. In orbit, there's one force acting on it. That's the force of gravity, and that's a centripetal force. It's towards the center of the circle, so it results in a centripetal acceleration. The gravity force can be calculated with Newton's law of gravity, m1, m2, big G over r squared. And the centripetal acceleration can be expressed as v squared over r. Again, the mass of the object in orbit cancels out, and I can multiply both sides by r to simplify that there. This leads me to find that the speed of an object in orbit is m2 big G over r, and I have to take the square root. And that is equal to v. So, one thing about satellites is that their speed is this. Once we know their speed, we can ask things about their kinetic energy. So kinetic energy is 1/2 mv squared. Again, this should look pretty familiar from the last problem. V, I'm just going to take this expression from over here and substitute it in for V over here. So there's my V, and it's being squared. Now, because I basically have a square root that's then right away being squared, those two effects cancel each other out, and I can simplify this a bit by writing, or by just getting rid of those two things. And these two m's are different. This m2 came from over here. It was the mass of the planet, because the mass of the satellite were these m's that canceled out. And this m over here is the mass of the object whose kinetic energy we're interested in. So that's the satellite. So we've got mass of satellite, massive planet. Those are very different m's, so I'll just make sure they're clearly labeled m1 and m2. Now, at this point, we have an expression for the kinetic energy that looks a lot like our potential energy formula. m1, m2, big G over r. Here's our potential energy formula. m1, m2, big G over r with a negative in front of it. So one way we can look at it is that this part here is exactly my potential energy formula, but it's missing the negative sign. So if I took my potential energy formula and I multiplied it by a negative, by -1, then those negatives would cancel out and I get exactly this thing in this green box. So this is basically negative of the potential energy. The potential energy itself is normally negative. So if I take a negative of a negative, that ends up being positive, and that's exactly what I have here. So what this means is that the kinetic energy is 1/2 times the negative of potential energy. Kinetic energy is negative 1/2 potential energy. And that is the funny thing about satellites. It doesn't matter where you want to put your satellite, whether it's in a low Earth orbit or a high Earth orbit, or whether it's orbiting at this distance of the moon. Once you know the height you want the satellite to be at, you know the potential energy, and you're going to have to give it the right amount of kinetic energy to stay in orbit. Too much kinetic energy, it floats off into space. Not enough, it crashes down to Earth. And the amount of kinetic energy you have to give it, it turns out, is exactly negative 1/2 times the potential energy it would have at that height. And this jives with what we found in our previous example. Here was our potential energy. And if we multiply that by negative 1/2, we get exactly this number here, our kinetic energy. So we sort of proved that it works by leaving all the variables in. And then we've actually already done one example with numbers to sort of demonstrate it. Now, this formula is not normally a formula I would give to students on a formula sheet if they're doing a test. It's sort of a very specific application. So what I say to students is, there might be the odd question on a test or a problem where knowing this is helpful, and you're free to use this fact if you want. But if you want to use it, you have to know it. You have to memorize it yourself. And if it comes up where there's a question about the total energy of a satellite or potential and kinetic energy of a satellite, and you don't have this formula memorized, that's totally fine, because you can just do what we did up here in the original example. You know how to find the speed of a satellite using circular motion. You know that kinetic energy is 1/2 mv squared, and you can calculate potential energy using this new formula. So there's no situation where you need to use this new fact, but it can be a shortcut sometimes if you want to use it as such. So, quick recap. Our old formula for potential energy worked when we confined ourselves to only working in areas where little g was a constant, like if we stayed close to the surface of the Earth. If we want to lift things really high through a range where little g changes, then we need a new formula because we won't have one value to plug in for little g. That new formula is this guy. Couple things to note about this formula is potential energy is now negative. That's totally fine because it's not something that actually exists. It's just an idea. Another thing is that as R increases, as we lift something higher and higher, this number actually gets smaller. So by making it negative, we actually have a smaller negative number, meaning potential energy is going up. And how high do we have to lift this object so the potential energy goes to 0? We have to lift it to a height of infinity. After that, we just did a couple examples, getting used to this new formula and sort of combining it with other formulas we had for kinetic energy and a little bit of circular motion, which we've been getting quite used to doing by now. So that should give you some of the understanding that's required to solve questions where we're looking at the potential energy of things that are really high above a planet and potentially even in some sort of orbit.